All right, good afternoon. Ready? So any questions before I begin?
Go
ahead.
Can you just repeat how do we know it's a odd function? Because in the homework we have that one that it's none, but I don't remember, like, I know how to make it even, like two, but no.
Okay, so odd means that when you plug in negative to the function, you get the same thing as taking your function and making it negative.
Okay,
So that's what you have to show for odd.
gotcha. Thank you.
Okay. Okay, we ended the class last time and I asked you to take a look. Oh, today we're doing optimization. Next time, antiderivatives. This is the last bit of material that would be on the test, but I'm really thinking I'm not going to put optimization on the next test. I'm thinking I'm going to put it on the final. So we would end, the material that would go on the test would end at probably 4.3. I'm not going to ask you to sketch a curve on the test just because of the time it takes. But 4.3 would be where the test material will end for next week. All right. And like I said, the review will be coming out the next probably day or so. So we're going to cover optimization today. On Tuesday, we're going to talk about antiderivatives. And then on Thursday, we take our test. All right. That's the plan. So at the end of class last time, I asked you to consider this problem where you had to build an enclosure where you had 4 identical pens, each with an area of 12 square feet, and define the dimensions which would use the least amount of material. So did anyone try this or take a look at it? I know you had other homework to do. No? Okay. All right, so let's do this. All right, let's do this problem. So I'm going to try and build this. There's many different ways that I could build these. All I need is that each one of these pens, right? Each one of them has to have an area of 12 square feet. That's a requirement here. So how I build this is up to me. What I'm going to do is I'm going to start labeling some things. I'm going to call this, well, you know what? Let's write our objective. Sorry. Our objective is to find the dimensions which use the least amount of material, right? So that means I want to have the smallest perimeter possible. Perimeter meaning, and when I say perimeter, I don't really mean outside of this. I mean all of these sides added up together. All right. Okay, so objective, sorry, it's my dog hacking on something. Stop, man. Find the minimum perimeter. And again, I'm using that word perimeter loosely here because I don't really mean the distance around. I just mean total sum of all the fences. So if I'm going to try and find the minimum perimeter, then I'm going to have to start labeling some things. So I'm going to call this X, which means that's X and that's X and that's X and that's X. And then this total distance here would be, let's call it Y. So what is the total amount of fence that I'm going to use? What is the perimeter? The perimeter will be what? You tell me.
P equals 4xy.
4, careful. 1, 2.
Oh, 5x, sorry.
5x. Then what?
Plus y.
Plus y, right? Plus there's only one. Remember, I don't have to build any fence along the river, only along the backside. So I'm going to have y, and then I'm going to have 1, 2, 3, 4, 5 x's, right? All right, that's my perimeter. I'd like to find when this is the smallest, but right now it's an equation with 2 variables on the right. I need to get it to a function of a single variable. So now comes the constraint. All right, so what is my constraint? I know that the area of each pen has to be 12, right? The area of each of these pens has to be 12. So the area, hold on, I gotta sneeze. Okay, I think that was it. The area of each of the pens has to be 12 square feet. How in the world can I represent that as a constraint? The area of one of these pens, right, has to be 12. So the area of that pen that I just showed you should be this distance right here, which I'm gonna leave as a question mark for now, times this side, which is X. So what is the length of that side there, that question mark? It's not
1/4
Y.
y.
It's one, what?
1/4 y.
It's a fourth of Y, right? Because each of these are gonna make up four of these. Was that?
Oh, sorry, I thought it was.
Can you all hear that? I'm in the middle of something, dude. All right. So this is 1/4 of Y, right? Because we're going to cut this Y into 4 equal pieces. So that means that X times 1/4 of Y must be 12. Another way I could write that is 1/4 X, Y equals 12. I'm going to go shut this door. Go drink some water. Okay, we good? Now, once I have this, I see that I have an equation with X and Y in it. I could solve this for X or Y. I'm going to solve for Y, and then I'll replace Y in that equation right there with whatever I get over here. So let me solve for Y. To get Y, I'm going to have to multiply both sides by 4, right? Which would give me 48. But then I have to divide both sides by X as well. That okay? Take that answer, plug it in over here. My perimeter will now be a function of X completely because my Y is going to go away and I'm going to replace it with 48 over X. All right, that's it. We've got our objective function. What's the next step? Once I have the objective function. Remember my poem, my English class when I was in middle school? Two roads diverged, right? You have to make a choice here. Is this going to be open interval or closed interval? So let's think about X. How small can X be? How big can X be? Well, I can make X as small as I want, but I can't make it 0, right? Because if it's 0, I will have no area. So my X has to be bigger than 0, but at the same time, I can make X really, really long and my Y's would be really, really narrow. I can make X as long as I want, right? Do y'all understand that? That's an important aspect of these problems. We did a problem last time where we were trying to build or trying to do a rectangle and we had a fixed perimeter. When you have a fixed perimeter, then you can't let one of them become infinite because you have a fixed perimeter. But if your area is fixed, then you can change the dimensions, you know, so that it's really long and really, really narrow. So this is going to got to be between 0 and infinity, or, you know, the way we normally wrote it was this. And that tells me right there, I've got to do the open method, right? I can't use the closed method. So this means I'm going to have to take the derivative, right? Get the critical numbers, but I'm not going to go plug those back into the function. I'm going to have to do a number line. I'm going to have to do test points. I'm going to have to look. And what we're looking for is where hopefully the function will go down then back up, right? Down then back up, because that's where we'll have a minimum. So let's go for this. Let's take the derivative. So we find the derivative of this function. So that was work on the side. So my derivative is going to be 5 minus 48 over x squared. This is similar to a problem we did last time. Like the derivative is very similar. Notice I'm just rewriting that as 48 x to the -1 and then taking the derivative, which means the -1 comes out 48 x to the -2. And so I've rewritten it that way. And now I need to figure out where's this derivative equal to 0 and where does the derivative not exist. Okay, so where's the derivative 0? I've got to take this, set it equal to 0. And this has been becoming a common theme here that, you know, we're going to get a common denominator between these two, put them together. So I will rewrite this as 5/1 and multiply by x squared on the top and bottom. That'll give me 5x squared on top minus the other numerator 48 over the common denominator x squared. When is that? 0. And a fraction can only be 0 if the top is 0. I'll move things around. So I add 48 and I divide by 5. And then I get my calculator out. Okay. I'm going to figure out what x is by doing plus or minus the square root of 48 over 5. So 48 divided by 5 and square root of that. I get about 3. Let's just round it. It's about 3.1. X is approximately plus or minus 3.1. Now I'm going to throw away the negative because remember, X has a restriction up here. We're only using positive X's. So X is approximately 3.1. That's our first critical number. Now, is the derivative ever 0? I mean, sorry, does a derivative ever not exist? Well, it's 0, right? But 0 is not in the domain, right? We can't plug 0 into this, but 0 is not in the domain to begin with. So nothing here. So I'm going to put my critical number down on my number line. It's my next step. I'm going to, wow, that wasn't very good. 3.1. And then I am going to put 0 here because I just want to remind you that there is nothing over here, right? You can't pick anything over there. So make sure your test points between here, you know, somewhere in here, somewhere in here, two test points. Look, the function can, it looks like, because we only have one critical number, it's looking very promising that it's going to probably go down and up, right? But we have to verify it. We actually have to prove it. So we have to go plug a number in here, like 1. Let me go with 5 here. And where do these numbers go? Drum roll.
And the derivative.
To the derivative. Because the derivative tells you where your function's going up or down, right? The derivative tells you positive derivative going up, negative derivative going down. So, right, remember I told you about my friend whose love for his girlfriend had a positive derivative, right? That guy was so full of shit. He was constantly cheating on his, I think it was his wife, man. It was bad. It was bad. Okay, anyway, we plug in 1 into the derivative. Where's the derivative? Here's a derivative up here. Let me grab it real quick. Okay, so I'm going to plug 1 into this. Let me just do it visually. If I plug 1 in here, 48 divided by 1 is 48. So 5 minus 48, that's a negative number. So I know that when I plug in 1, I'm getting a negative number here, and that tells me my original function. Oh, you know what? I used f instead of p. Oops, let's change it. P prime, p, sorry, I forgot what I was doing. So p prime, p is going down. Where else do I need to change it? I did it right here, p, and see, I got distracted by my old office mate. Okay, if I plug in 5, I should get a positive number. Right, I should get a positive. You can check it for yourself. And that would tell me that my original function is going up. And that's good because that's what I was hoping would happen. The function goes down and then goes back up. So I know that that's a local minimum, but I also know it's the absolute minimum as well, because my function goes down and back up and never comes back down. I'm never going to have a lower point. That is the lowest point. So I know I have a minimum, right? I have a minimum at x equals 3.1. Well, if I know what x is, now I should be able to get y. So y is equal to, and just it's right here. I can see it right there, right? That's what y is equal to. That comes from the constraint. The constraint will always help you get the other variables. So I'm just going to take 48 and divide it by 3.1. 15, we'll round 15.5. All right. So let's see if we've answered the question. All right. The question was, find the dimensions which uses the least amount of material. I've done that, right? I have found that x here, this side must be 3.1 feet, and that this side needs to be 15.5 feet. Okay. If I do it that way, I will use the least amount of material. The second part of the question asks, how much material would you need? So I need to actually figure out how much fence that is, right? Which is actually the original objective, right? The objective was the perimeter function. If I replace x with 3.1 and y with 15.5, that will tell me the total amount of fence, the perimeter that I'm going to need. So let's plug that in. So to answer this one, what I'm doing is I'm doing p equals 5x plus y, which is 5 times 3.1 plus 15.5, which is 15.5, 30, 31, I think. Is that right? Someone check me. 31 feet?
Yeah.
31 feet. So I'm going to go to the store and I'm going to buy 38 feet because I'm going to screw up, right? No, I'm going to buy 31 feet because I'm going to make it. I'm not going to make any mistakes. But 31 feet of fence is all I need. I will create 4 identical pins. Each one of them will have 12 square feet. And that is the least amount of material I can possibly do this with. Right? It's the absolute minimum perimeter.
I have a question.
Yes.
So going back to that 3.1, you said that it's a local max, but you know for a fact it's an absolute max. Is that
No,
because,
minimum.
sorry, min. I'm so
Yeah.
sorry, minimum.
I knew you meant that.
Is that because it's the only critical number we have that you could, like, how do you know that's not just a local?
Yeah, because it's the only one critical number, and it going down and up means that so think about it. I think you understand, but think about it. What we're saying is this: at 3.1, if we were to graph this function, it goes down and back up like that, right?
Yes.
Okay. If there was a lower point anywhere on the graph, if there was, like, let's say there was a point lower over here, I would have to get to it, right? Which means I'd have to come back down and back. I don't necessarily have to go back up, but see, I would have to come down again and back up. See, here I go down and up, but if I had a lower point, I would have to go down and up again, somewhere else.
Right.
And since this is the only critical number I have, I know that nowhere else does it change and go down up again.
That makes sense.
Okay. What would be incorrect, and I think I warned you all about this, is on a test, if you find the critical number and you say, oh, that's a minimum, and you don't do any of this, that would be wrong. because you have found a critical number, but you have not shown me that that is the that is a minimum. It could be a maximum. You don't know. Now within the problem, it probably makes sense that it should be a minimum, but you still have to show it. Okay, we good? So I've given you a couple of problems now with optimization. This is last class. We started this whole thing out with a rectangle, and we were like, hey, how should I make it so I have the most area? And we did another one, you know, where was it? I thought we did another one. Yeah, we did this one. So we've done a lot of things that have been pretty visual so far. We're going to do another problem now, and let's just see, okay? Let's see how similar it is to that one, to what we've done. A can must hold 1 liter. Find the dimensions of such a can with the smallest surface area. Now, when I say can, I mean like an aluminum, like an aluminum cylinder, like a cylindrical can. All right. And we're just going to take, we're not going to think about, like, modern day aluminum cans are not perfect cylinders, right? Cans are kind of complicated, aren't they? Cans have, like, I have a can here. Don't cans have like a little indentation on the bottom, right? And they're not perfect cylinders. For this problem, we're going to act like it's a perfect cylinder. And what we want to do is we want to make a can that holds 1 liter, but do it in a way that we use the least amount of material, so it has the smallest surface area. Think about this. This would be a practical problem if you were making aluminum cans, right? Like if you were making, let's say, 12-ounce cans, it doesn't even have to be a liter, just any amount of material or liquid in there. The way you make the can is going to impact the cost, right? Because aluminum costs money, and you want to use the least amount of aluminum to make the can. So there's a lot of different scenarios that we could have with this. So what I have, y'all can see this, okay? This is a visualization of a can, okay? We have this 3-dimensional can here. And right now I have the computer it's fixing it so that holds 1 liter, okay? So that can that I'm showing you there holds 1 liter. But I'm going to show you that I can build a lot of cans that hold 1 liter. I could make the can really, really flat like this, and that still holds 1 liter. Or I can make it like this, really tall and narrow, and that still holds 1 liter. But notice this red number right here, surface area. Notice how the surface area changes as I change the shape of the can. Right now the surface area is 677. If I go here, look, it got smaller, right? So that's using less material. And then I get smaller, and then watch what happens. 550 up, it's going back up, 600, 700, right? You would not want to make a can like this for several reasons. One is you're using a lot of material, and then other, people don't want to walk around like that, taking a sip out of their soda can, right? So we want to do this in the most efficient way possible, right? That's the goal. All right, so let's do it. Where do we even begin? So let's start with an objective. Our objective we want the smallest surface area, right? The smallest surface area. We want to minimize or minimum surface area. We want the minimum surface area possible, right? So we need a formula for the surface area of a can. Now I'm just going to put S for surface area. What is the surface area of a can? Well, we need to draw a can. So what is the surface area of this? Well, we would need to know the radius. We'd need to know the radius of this can. And we would need to know the height of the can. If those two things were given to us, then we should be able to find the surface area. Does anyone know the surface area formula for a can?
Would it be 2 pi r times h plus 2 pi r squared?
How are you getting that?
Well, I figured that if I do 2 pi r, then that should give me the circumference of the circle, or of the top of the can. And then if I were to grab the sides of the can and expanded it into a flat surface, that would just be a rectangle with a length equal to the circumference of the circles at the top and the bottom of the can.
Yes, yes, and yes. Let me do that a little slower. Okay, so we can all follow this. First things first, the top of the can, right, is a circle, right? And the bottom of the can is also a circle. And the area of a circle is pi r squared. We should all be comfortable with that, right? Pi r squared. So I know that the surface area is going to be the pi r squared from the top circle and the pi r squared from the bottom circle. So I should have two of those pi r squareds in my surface area formula. Agree? Okay. Plus, now I need to count this outside of the can, right? So what Robert was suggesting was that if we think about a can, if you can see my camera, we think about a can, we've already taken care of the top and the bottom, right, of the can. If we imagine the rest of it, cutting it down the center and opening it up, then it's just a rectangle, right? So if we open this thing up, okay, take it, cut it, open it up and lay it out flat like this, the distance from here to here is still the height, right? But the length of it is actually the circumference of the circle, the distance around the circle, because when you lay it open, that's how long it is. So this should be the circumference of the circle, which is 2 pi r. There's a formula for that, which means the area of this should be 2 pi r times the h, length times width. So plus 2 pi r h. Now this formula is in your formula sheets. No, it's not. Why isn't it there? Why do they give you the volume and they don't give you the area? That's really weird. I've never noticed that before. Interesting. Okay. Well, that's the surface area of a cylinder, right? Understand? Any questions? You could always look it up, right? If you needed to, what's surface area of the cylinder? All right, so that's my surface area formula. Let me put it over here. 2 pi r squared h. I'm sorry, not h. 2 pi r squared plus 2 pi r h. I would like to know the minimum of this. That formula has two variables in it. It has r's and it has h's, right? Well, it only has one h, but it has r's and h's. So this is kind of like before when we had x's and y's, right? And we needed to get it to a single variable x. Here we have the thing we're trying to find the minimum of, and it has two variables in it, r and h. And so if I have any chance of doing this, I need to get that to a single variable. So I think maybe now we should talk about the constraint. The constraint on this is that the volume of this has to be 1 liter. And I've already told you how much a liter is. A liter is 1,000 cubic centimeters. That is the restriction, right? But what is the volume of a can? Well, the volume of a can, we can look up the formula. All it is the area of the top of the can times how deep it is. So it's just this top area times the depth. So the pi r squared is the area on top times how deep it is. That must be 1,000. Now I have a constraint equation. I can solve this equation for either r or for h. It's up to you. Looking back at this, what would you rather have in here? Would you rather replace the h or would you rather replace the r? Or look at here, what would you rather solve for, h or r?
H.
H.
H probably, right? Because if you solve for r, you'll have to take a square root. So I'm going to try and avoid that. So if I solve for h, I'm going to take the 1,000 and I'm going to divide it by, well, pi r squared, right? Now I have an equation for h, right? I can come back up here and replace that h right there with that expression. So my surface area is 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Some things clean up here. Let's try and clean this up. I know it looks terrible right now, but okay, what can happen here? I think a pi goes away, right? A pi cancels. This r cancels with one of those r's. I can multiply the 2 times 1,000 to get 2,000 on top. So I'm going to have plus 2,000 over r. It's not terrible, right? It's not terrible. And that is now, my surface is now a function of r, right? So I have it down to a single variable. And so what's left for me to do at this point?
Divergent paths.
Yeah, which way are we going? Open or closed here? So think about the variable here is r. Are there any restrictions on the radius of this can?
Cannot be 0.
Can't be 0. And can it just be as big as I ever want it to be?
No.
Well, I mean, I wouldn't want to do that, right? But could I make it like 20 feet wide and then have this really, really thin can and it still holds 1 liter?
Yeah.
I mean, I could, right? So I'm going to say it can't be 0. Why can't it be 0? Because if it's 0, I have no can. And you must have 1 liter. See, the 1 liter must always be there. So I can't be 0, but I can be as big as I want. So this is another open interval, 0 to infinity. That sucks. Well, does it suck? It's not that bad. It's not terrible, right? And now we're there. We're ready. Just derivative, set it to 0, figure out where it doesn't exist, number line, test points, blah, blah, blah. All right, let's look at the derivative. The derivative of this function, s prime of r. Okay, so r is the variable. 2 pi is a constant. Derivative of r squared is 2r. So I'll bring the 2 out. It'll become 4 pi r. And then the 2,000 over r is the same as like 2,000 r to the -1. I'll bring the -1 out. 2,000 over r squared. So I want to know when that's 0, and I want to know when that doesn't exist. The only place it doesn't exist is at 0, but 0 is not in my domain. So I'm going to just chunk this one. Is that clear to everyone? I can't plug 0 in here. I get division by 0, but 0 is not in the domain. Setting it to 0, on the other hand, is going to be very much like the last problem. 4 pi r minus 2,000 over r squared equals 0. We get a common denominator, r squared on top and bottom. Wait a minute, that's 4, that'll be 4 pi r cubed minus 2,000 over r squared equals 0. That can only be 0 when the numerator is 0. And now I just need to solve for R. All right, when I solve for R here, I'll move the 2000 over. Right, move the 2000 over. And divide both sides by 4 pi. Which I believe just comes out to be 500 over pi, right? 500 over pi. But I need to solve for R, right? So I'm going to have to take the cube root on both sides, the cube root. And when I do cube root, I do not have to do plus or minus. So that is my critical number. Now I need to have some idea of what that number is. So I'm going to get on my calculator. I'm going to do this. 500 divided by pi. And then I'm going to take the cube root of that. So I get that R is approximately 5.4193. I'm going to round it to 4 decimal places. That's my only critical number. So I'm going to go to a number line now. Trying to fit this all on one page. So now I'm going to go to a number line. I know that at 0, nothing can happen over here. And at 5.4193, I have something happening. So I need a test point. Let's go with 1. I know that that's not where 1 is. It doesn't look like that's where 1 is, but I'm just picking a number to the left and to the right. And what are we hoping to see? Down and up or up and down? Minimum surface
Down
area.
and up.
Down and up.
So we went down and up. That's what we're hoping for. So I'm going to take 1 and plug it into what?
Derivative.
The derivative. So I need to know what is S prime of 1. I need to know what S prime of 10 is. My derivative, I'm highlighting in green. That's what I'm about to use for this. All right, if I plug in 1, I get 2000 here. 4 times pi times 1 minus 2000, that's negative. Which means my original function is going down here. S is going down. And then if you try 10, it will work out to be positive, so S goes up. Which means my surface area then goes back up. So I found a minimum, right? So minimum when R equals 5.4193. So tell me what H is then, right? Because right now you've told me to get the minimum surface area, your radius has to be 5.4193. But then what would the height of the can be? Well, the height would be, well, I can see it. It's right there. See that? You know, from our constraint, I can see my equation for height. My height will be 1000 over pi times 5.4193 squared, which is approximately, calculator time. Are y'all enjoying this? Ten point 10.838. I'll go one more decimal point. 84. And this will be in centimeters. Both of these are in centimeters because when we were looking at the original volume, it was 1,000 cubic centimeters. So this is the measurement of each of these lengths, centimeters. Have we answered the question? Can must find the dimensions of such a can with smallest surface area. We have found the dimensions of the can. Okay. Does anybody see that there's actually a connection between these two numbers? Do y'all notice anything?
It's double the amount.
It's double, right? It's saying that the height should be double the radius. But wait a minute, isn't radius half the diameter? So like think about the can. The can looks like this, right? What they're saying is that whatever this height is, right? That height is twice as much as the radius. So this right here is double the radius, right? Is the diameter, which means that if you're going to do this the most efficient way, you want your height and diameter to be equal. That's the best way to do it. Now, when you have a can, like a soda can, the height and diameter are not the same, right? We don't do it this way. If you go back to like the 1950s and you look at like old oil cans, metal cans, the height and diameters were the same. And it's because those are like true cylinders, and that's the way they did it. It was the most efficient way to do it. Now there's a lot of other factors when we build it, when we make a can. I mean, they're not perfect cylinders, number one, but also, you make a unique can, something, narrow and tall, and you distinguish yourself from other cans, right? So there's that, what do you call it? I'm not sure what the word I'm looking for is. The strategic, advertising, or not advertising. What is the word I'm looking for? Business people would do this, right? They would think about how to make, like Red Bull, right? Has a distinct can, right? You know it when you see it, right? It's a different shape, different dimensions. Sometimes it's worth paying more to have a can made that way because you will stay in business than to have just a generic can that looks like every other can, right? So there are other factors at play there. Okay, but mathematically, this is the most efficient way to do it. Questions there? Find the point on the graph y squared equals 4x minus 1, which is closest to the point 3, 1. I'll let you jot that down. I'm gonna go graph this for us so we can see it. Actually, I have it made already, so maybe we should do it that way. There's the problem. I'll put it back up in a minute. So what you have is this is a parabola that opens sideways. This would be something we talked about in college algebra. This is a sideways opening parabola. And what we want to try and figure out is which point on that parabola is closest to the point 3, 1. So this point in blue is the point 3, 1. The red curve is the parabola. And so if you can imagine, all these different points that are on that red curve, you're trying to find the one point on the red curve that is closest to that point 3, 1. So obviously it's not over here, right? That one's really far away. And then, how about straight up? Is that the closest? Straight up? It's close, but it's not the closest, right? How about straight over like that? No, right? It's somewhere in here, right? Somewhere in here is the closest point. I would like to know exactly what that point is, right? Now, if you want to think about the relevance of a problem like this, imagine that this point is Earth, and imagine this is some meteor headed towards Earth. See, we can look at the motion of a meteor, and we can actually create the function, the path that it's traveling on, and then we can then predict how close it's going to get to us. So the way we can do it is by finding a minimum distance, just like this. When you say it that way, it's a little more applicable, right, than what I'm doing here. All right, so let me show you the solution first. This is the point right there. That's it. Okay, that is the solution. How in the world are we going to do that though? All right, right? It seems like, how are we going to do? We were building pins like up against rivers, and now we're doing this. This is weird. All right, so we first have to have an objective, right? The objective is to find the point on the graph which is closest, right? Closest. What does that make you think? We finding the maximum or minimum of something?
Maximum?
Maximum, max what then?
Great question.
We're talking about the distance between two things, right? Talking about the distance between a graph, a curve, and a point. The point that's closest, right, would have the shortest or smallest distance between the two, right? So we would want to find, the objective would be to find a minimum distance, right? We're trying to find a minimum distance between two things. I'm going to draw just a real quick rough graph again. Here is 3, here's 1, here's the point, right? Here's the point I have, 3, 1. And then I have this parabola, right? Ooh, where'd it go? I have this parabola that goes like this. So I would use a graphing utility. If I were doing this problem like out of a textbook, I would use a graphing utility to help me graph it. Okay, so we have this parabola, goes like this, comes through, goes like that, and it goes forever in that direction like that. And so what I'm trying to find is the minimum distance between this point, right, 3, 1, and the red curve. So what I'm going to do is I'm going to draw an arbitrary point on the red curve, just anywhere. Okay, I'm not going to draw the one that's closest. I'm going to just pick like an arbitrary one, like right there. That point is on the curve, right? But it could be anywhere on the curve, but I drew it right there. We are trying to figure out if we can measure the distance between that. Let's call that D. And we want to see if we can get D to be as small as it can possibly be. Does that make sense? So we want to now, let me update my objective. We want to find the minimum D, right? The minimum D possible. Well, what is D? D is the distance between these 2 points, right? So this point here that I drew that was arbitrary, it has some X coordinate and some Y coordinate. I don't know what it is, right? But do you agree it has an X and a Y? What is the distance between 2 points? Do you remember a formula in college algebra that gave you the distance between 2 points? I know you did it at some point. It's in our formulas, I hope.
The M.
Is it what?
The M, the
M?
dependent, yeah, like Y2.
Yes, yes. That is,
Y2 minus
oh, here
Y1.
it is. Yep.
Okay.
The distance between 2 points. I'm going to copy this. So I know from college algebra that if I'm given 2 points, x1, y1, and x2, y2, that the distance between them is x2 minus x1, that quantity squared, plus y2 minus y1, that quantity squared, take the square root. Now, for me, for this problem, let's call this first point, let's call it 3, 1, because that is the point that I know, right? And this other point, I'm calling it X and I'm calling it Y, right? And then just use this formula. So the distance will be the square root of, let's see, x2, which for us is x, minus x1, which for us is 3, that quantity squared, plus, all right, y2, which is y, minus y1, which is 1, that quantity squared. So let me recap. We have a curve and we have a point. Our objective is to figure out the point on this graph that is closest to this one. So I want to somehow minimize the distance between 2 points. I drew a picture from our point to some arbitrary point xy, and I came up with a formula for calculating that d. And now I want to see if I can get d to be as small as possible. But what's wrong at this point? Why can't I do this yet? What's wrong with d?
Multiple variables.
Yeah, it has x and y in it, right? It has x and y. And that we can't do that. We can only do this if we get it to a single variable. So we haven't used a constraint yet. Okay. Now the constraint here is hard to see. All right. It's hard to, well, I'm not going to say it's hard to see. It's tricky. It's not like the other ones. You know, the other problems, we had a fixed area, or we had a fixed volume, or we had a fixed perimeter, and that was our constraint. Here, our constraint is something hidden. It's kind of right in front of us, but also like not in front of us. Right now, we have x's and y's. I'd like to have just x's or just y's. So I need to somehow substitute one of these out. Do y'all see something that I can use to do that?
The graph itself, the formula.
What do you mean the graph itself?
Well, the graph itself. Well, not the actual picture of the graph, but I guess the formula for the graph.
Yeah, the equation of this graph
equation,
right here, right? That equation actually is a constraint. It tells you the relationship between x and y, doesn't it? This gives you a relationship between x and y. See, this point that we picked here in yellow, this point xy can't just be any point that it ever wants to be, right? It has to be on the curve. And if it's on the curve, then it must satisfy this equation. And since we have this equation that connects both x and y together, I can solve it for y or for x. What would you like? Do you want to do y and do the square root, or would you rather just move things around and have the x? Totally up to you. Let's solve for x, please. Yes? Okay, let's solve for x. Let's solve for x. It's easier to solve for x. So I'm going to move down here with my constraint. Let me copy this and just paste it down here. So my constraint is this. So if I now take that constraint and continue, let me add 1 to both sides. And then let me divide both sides by 4. So I know I could put that whole thing over 4. Well, I will. Okay, y squared plus 1 over 4 equals x. But I'm going to do it this way. I'm going to write it as 1/4 y squared plus 1/4 equals x. And the reason I'm writing it that way is because in calculus, we like this, right? We like to have numbers out front and then, you know, our variables to power, so that way, if we need to do a derivative, it'll be easier. Questions on the constraint? I've solved for x, right? So I'm going to go back up to this and I'm going to replace that x with it. All right, d equals the square root of, this is going to be ugly, in parentheses, 1/4 y squared plus 1/4 minus 3 squared plus y minus 1 squared. Let me just double check that. Yes, okay. Everyone see that I replaced the X? Here's where the X used to be. Now it's that. Is our objective function now a function of a single variable? Yeah, y, right? It's a function of y. So I can rewrite this as d of y equals square root of, let me try and clean this up. 1/4 y squared minus, I could put the 1/4 minus 3 together. That would become, I believe, 11/4 squared plus y minus 1 squared. So I just did 1/4 minus 12/4, which gave me negative 11/4. There it is. There is my objective function. I just need to now know if I'm going to do an open or closed interval. So are there any restrictions on y? Are there any restrictions on y? Think about the point here as it moves along this curve. Think about the y coordinate. The y coordinate can get bigger and bigger and bigger and bigger and bigger, right? Or the y coordinate can come down, 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 right? So there really is no restriction on y. So unfortunately for us, this goes from negative infinity to infinity, which means we're going to need the open interval. What do y'all think? Give me, I mean, just what do y'all think? Are y'all look like it's almost the end of the semester. That's the way you look. How do you, does this seem really hard? Like,
there are a lot of considerations that you need to take into.
yeah. I mean, these word problems, right? Word problems. I mean, this is always an issue, right? Well, the derivative, right? This derivative looks terrifying. Up to this point, everything's been, we've been playing nice, haven't we? We've been playing real nice. We don't get to play nice now. We have to take derivative of this. Let's not be intimidated. We can do this. We're about to be Cal 2 students. So we should be able to take derivative of this. So d prime of y equals, all right, what I see first is that I have a square root, right? And I know the derivative of the square root of something is always 1/2 times the square root of that something. Okay, I'm going to write that down. 1/2 times the square root of that something. 1/4 y squared minus 11/4 squared plus y minus 1 squared. All right, that's the derivative of the square root part. Now I have to go inside and take the derivative of what's in here. Now I have an addition sign, so I can do these separately, can't I? So it's actually not going to be as bad as it looks, but whatever I get, right, it's going to be the derivative of this one plus the derivative of this one. Can I do the second one first? Is that all right with you if I do this one? Do y'all see that that's just a little chain rule? 2 comes out. Y minus 1 to the first power times the derivative of what's inside, which is 1 because we're differentiating with respect to y because y is the variable here. So that actually isn't that bad, is it? For the derivative of this one? This one is a little bit worse, okay, but it's still not absolutely terrible. 2's here, so bring the 2 out. We have 2 1/4 y squared minus 11/4. Okay, that's the 2 coming out. This to the first power. Now the derivative of what's in here. What's the derivative of what's in here?
1/2 y.
1/2 y.
Half y. That's not that bad, right? I mean, I know it still looks like horrible, but it's not that bad. It's not that bad. Let me see if we can clean this up. I'm going to need a new page, so let me copy this. All right, some things I see happening here. This 2 and this half go away. And I can distribute the y through. And then I can distribute the 2 through. Okay, so what will that be? That'll be 1/4 y cubed minus 11/4 y plus 2y minus 2. Right? And then let me do this. D prime of y equals, isn't it all of that over 2 square roots of all that junk? 1/4 y squared minus 11/4 all that squared plus y minus 1 squared. Isn't that what it is? All right, all I did was just slid this whole thing on top of that. There's our derivative. We need to figure out where it's 0. And we need to figure out where it doesn't exist. Well, it's already a fraction, right? It's already a fraction. So all I have to do to figure out what the fraction, when the fraction is 0, is just set the top to 0. We'll get to the doesn't exist in a minute. Hey, I just realized we could put these two together. Sorry, I should have cleaned that up a little more. Do y'all see I can put those together? They're both y's. So get a common denominator between those. And I believe you get -3/4. -3/4 y. So 1/4 y cubed minus 3/4 y minus 2 equals 0. So I need to solve that. Pause on that, okay? Pause on that. We'll talk about that in a minute, because that's not a quadratic. You can't use quadratic formula, right? But what about where it doesn't exist? Where it doesn't exist would be is if this under here was ever negative or ever 0. Do y'all agree with that? This must be greater than 0, right? It can't be negative and it can't be 0. If it's 0, we'll have division by 0. And if it's negative, then we're trying to take the square root of a negative number. But this can never be negative and this can never be 0. You know why? What is this? What is all of this? Isn't that just the distance formula itself? Isn't that the distance formula? And the distance must always be bigger than 0. Look, I mean, we're talking about the distance between this point and that curve. That distance always has to be positive because the point doesn't lie on the curve. So I don't have to worry about this at all. This is true. So that gets me back to this. I need to solve this. And I have good news and bad news. Okay. The bad news is we can't solve that. Not with anything we have. We don't have a way of solving that. You could try synthetic division and all that. It's not going to work. Okay. We have run into an equation for the first time in this class that we can't solve. The next section in this class is called Newton's method. We do not cover that section. All right. The reason we don't cover it is because what that section does is it shows you how computer scientists program a computer to solve this equation, to solve equations in general. And they use a thing called Newton's method. So I know a lot of computer science people would love to see that. All it is an algorithm that was developed by Isaac Newton. And I can show you quickly how it works if you'd like to see it. Would y'all like to see visually how it works? Okay, let me first go solve the equation. Okay, so what I'm going to do is I'm going to solve this equation by going to, let's go to Wolfram. Okay, I'm gonna go to Wolfram. I'm gonna type this in here. Solve. Why are you doing that, man? What the hell? Solve, okay, there we go. Solve y cubed over 4 minus 3y over 4 minus 2 equals 0. I think I typed that in right. What, that was you. Oh, wait, no, I didn't type it in right. Sorry, forgot something. Oh, no, that was it. Never mind. I apologize. That was it. Okay, so it gave me some crazy shit. And so I'm gonna hit approximate forms that will give me a decimal. 2.4920. 2.4920. So y is equal to 2.4920. What did Wolfram just do? Right? What did Wolfram just do? So pause again. Let's go look at Newton's method. And let me show you what Newton came up with. So Newton, and I've got to go through this quickly. Newton said, hey, let's say you're trying to solve an equation. All right. So Newton's like, hey, let's say we're trying to solve some equation. X squared minus 2 is 0. All right. Let's say we're trying to solve that. What he did was realize, you know what? You could look at the left side of this equation as a function, right? And then if you're setting it equal to 0, then you're really just trying to find the x-intercepts of the function, aren't you? It's really what you're doing, trying to find the x-intercepts of the function whenever you're trying to solve any equation equal to 0. So the way he found the x-intercepts is this. He said, imagine you have the curve, right? Here's the function. And what we're trying to do is we're trying to find, what's going on, Robert? We're trying to find this point, right? Okay. So think like a computer thinks right now. Somebody has given us a function, all right? So we have f of x, we put that into the computer. And now what we're gonna do is try and figure out what value we need to plug in to get 0. So the first step is we're going to take a complete guess. We're just going to guess the number. Okay, so I guessed 3. Okay, you plug 3 into the function and it turns out that 3 doesn't work because when you plug in 3, it spits out a positive number. It doesn't spit out 0. With me? Now what we're going to do is at that point, we are going to draw the tangent line. And wherever that tangent line hits the x-axis, that's our second guess. So now we're going to guess at that point. And we're going to be wrong because we plug it in and we get a positive number. But then we're going to take the tangent line at that point and see where it hits the x-axis and use that as our third guess. And do y'all see what's happening? I'm going to zoom in. Do y'all see what's happening every time I do this? I go up, I take that tangent line, I come back down, and now I'm even closer. So I do it again. And you just keep doing this iteration over and over in the computer. And what's happened is we started out here at 3, and then we started to move closer and closer and closer to the real solution. The more iterations you do, the closer you get to the real answer. And that's exactly what Wolfram Alpha did. I put in the equation, it took a guess, and it started to do, well, some version of Newton's method. There's even more powerful methods, but that's basically it. But it uses the tangent line, which is kind of cool, all right? So the algorithm to do that, if you want to see it, this is the algorithm. I use my own algorithm here, but it's just a for loop. And I had it, I can do this for any equation. So what's our equation? It was 1/4 y cubed. So I'm going to use x instead of minus, what was it? 8/4? No.
3/4.
3/4. And then minus 2?
Yeah.
Okay. So I'm gonna have this do this. It's gonna do, whoa. I must have not, oh, I forgot the x cubed, sorry. There we go. Okay, so look, I had it do a guess. I had it guess, what did I have it guess? I had it guess a solution of 2. Now, I haven't given you the algorithm. The algorithm is Newton's method. I'm not going to get into the algorithm. This is just the code for it. But you can see what it did. We took a guess, and then after the first iteration, it was at 2.5, and then 2.4921, then 2.4920, and then it's there. Do you see? It's there. I mean, it got to it. Let me do a guess further away. Let me see if I guessed at 5. There we go. So I guessed at 5. After the first iteration, I was at 3.5, then 2.8, then 2.5, then 2.49. Up, one more. Boom. This is pretty much what Wolfram gave us, right? It converges very fast to the answer. Okay, so we are now back to this, all right? I would never give you a problem you can't solve, all right, on a test or something like that. But this was an opportunity that if I did cover Newton's method, this is a perfect opportunity for me to say, hey, we don't know how to solve this. Next section, we will actually see how to solve it, and I give you the answer. So we're just going to take that on what I've just shown you, and we're going to go to a number line. We're going to put 2.4920. We're going to remember that there are no restrictions, right? There are no restrictions. So I need a test point, something over here. How about 0? Test point over here, how about 10? And these are being plugged into the derivative, right? The derivative. So I need the derivative at 0, and I need the derivative at 10. Now, I don't want to do this because I don't feel like plugging it in, but I will tell you this. Here's the derivative. I will mention this. The denominator of this derivative is always positive. This is always a positive number because it's the distance between two things. So all you really have to do is figure out what happens when you plug them into this, into the numerator. Without actually showing it, I will tell you that this does go down and then it goes up. So we have found the minimum. So this tells me that y must be 2.492. And once I know what y is, I can go get x. How do I get x from y? Go back to the constraint. The constraint. Here's the constraint. We had solved for x. Plug in the y value here, and we get x. Did this just get very complicated very quickly here? Like this example, right? Okay, I'd like to do another problem. I have maybe enough time for one more. I guess we want to know what the final answer of that was, huh? I think I have it. The solution to this is y was what, 2.49? I rounded it to 2.5, and the x value is 1.8. That point right there, that's the closest point to 3,1 on that graph. Thought I had another problem. I guess not. Okay, I'm trying to debate what I show you next. Do I show you the cylinder in a sphere, or do I show you the wire problem? Kind of feel like doing the wire problem. Let's do the wire problem because it's more connected to what we talked about last class. Do you remember me asking or talking to you about this last class, that let's say that you had a table that was a rectangle, or let's say a square, because we did prove last class that with a fixed perimeter, a square is gives you the most area, right? For if you have a rectangle, to get the most area, it needs to be a square. I did show you that. So let's say we have a square and let's say we have a circle, and that the perimeters of both of these are the same. So that means the distance around this square is the same as the distance around this circle. Which one of these would have more area? Right, and I told y'all it was a circle. But now I want to prove it to you, all right? So the way I'm gonna do this is gonna look totally crazy when you see it the first time, all right? I'm gonna try and prove to you that the most area you can ever get if you have a fixed perimeter between a square and a circle is to create a circle. So the wire problem is what this is called. You're like, wire? What does a wire have to do with this? All right, so let's imagine that I have a wire, okay? Something flexible. I have this wire. And let's say it has a fixed length, and it doesn't matter how long. I can leave it as a variable. I'm not going to though. I'm going to just say, let's say this is 10 feet long. All right, I'm just going to assign a value to it. All right, so what I want you to do is this. I want you to come in here and I want you to cut the wire somewhere. Okay, I want you to cut it right here. And out of this first piece of wire, I want you to make a square out of it. So I want you to bend it and make a square. All right. And then out of the second piece of wire, I want you to bend that and I want you to make a circle. And then the question is, how do you cut it so that the total area of both the square and circle is as big as possible? How do you cut it so that the total area of both the square and circle together is as big as possible? So think about this. Think about this. One scenario is that I don't cut it at all. Okay, so if I don't cut it, I'm either going to make a square out of it or a circle, like all square or all circle. Does that kind of make sense? Like we have to pick a distance. We have to figure out where do we want to cut it? Like we're going to cut it somewhere. Hey, let's call this X. Let's say X is where we cut it. If X is 0, then everything is going to be circle. If X is 10, all the way to the other side, everything's going to be square. So it's kind of like to the left of X, to the left of the cut is the square, to the right of the cut is the circle. Making sense? I know this seems like a weird way to show that the area of a circle is better than the area of a square, but it's going to. Watch. So let's try and find our objective. Objective is to find the maximum total area, right, of both together, which means you need to tell me what the area of each of these are. So what's the area of the square? Should I draw the square? Yeah, let me draw it. I bent the metal, I made the square. Over here, I bent the metal and I made a circle. So what is the area of the square? I'll do AS for area of square. And then over here, I'm going to say, what's the area of the circle? So can anyone tell me the area of the square? You need to know the sides, the length of the sides, don't you? So what are the lengths of the sides? How long is this?
X long? No, it wouldn't be.
Almost.
It'd be a fourth X long.
Why is it a fourth X?
Because if that X is the entire perimeter of the box, then each side would need to be equal, I guess.
Yeah,
That
you're bending it, right? You're taking the wire, it's X long, and you're bending it into a square, which means each side is 1/4 of the total distance, which is 1/4 of X. So this is 1/4 X, this is 1/4 X, this is 1/4 X, and this is 1/4 X. So the area of it is just two of the sides multiplied together. So the area of this square should be 1/4 X times 1/4 X, which would give you your 1/16 X squared. That's the area of the square. Yeah? Now, what about the area of the circle? This is harder because what we know, the only thing we know is the distance around it. How long is the distance around that? What's the circumference of this thing?
10 minus X.
10 minus X. That's whatever was left over after you cut, right? So to the left of the cut is X. Whatever's left over is 10 take away X. Right? Now we know the area of a circle is pi r squared, don't we? We do know that, but we don't know the radius yet. We should be able to figure out the radius because how is the circumference related to the radius? Circumference is 2 pi r, right? That must equal 10 minus X. And I can solve that for R. R is 10 minus X over 2 pi. So I just divided both sides by 2 pi. Which means the area of the circle is pi times 10 minus X over 2 pi. That's my R squared. Who has a question? Let's get back to the objective. I wanted to find the maximum total area. Where the area, the total area, should be the area of the square plus the area of the circle together. That area should be 16x squared, right? Plus pi times 10 minus X all over 2 pi squared. And that is already a function of a single variable, right? Isn't it? So I should just write a of X. So now we have to choose open or closed interval. Is there a restriction on X? What's the smallest X could be?
0. Well,
0.
1.
And then we're making, no, it could be 0, but
0.
then we're using the whole wire for a circle, right? Or it could be 10, but then we're using the whole wire for a square. So I have a closed interval this time, 0 to 10. Before I take a derivative, I'm going to clean this up. Let's see if you can keep up with this. On this function, instead of doing this thing squared, I'm going to do squared on the top and squared on the bottom. And what that allows me to do is write this as 4 pi squared on the bottom. And what that allows me to do is cancel one of the pi's, which means that my area function looks like this now. A of X equals 1/16 X squared plus the pi canceled, but I still have a 4 pi on the bottom. So I'm going to write 1 over 4 pi. And then I still had the 10 minus X in that quantity squared. So I had the 4, one of the pi's on the bottom. I put it as 1 over 4 pi out front, and I still had 10 minus x squared, so I put it there. And this is going to be on the interval 0, 10. And I think I'm okay taking the derivative of that. I think I'm feeling all right about this derivative. I'm going to do this on the next page. Any questions about this algebra? Derivative time. The derivative of this is 1/8 x. That's just power rule there. Here, I'm going to have 1 over 4 pi as a constant. It'll come for the ride. The 2 comes out, and that creates a 1 over 2 pi because the 2 and 4 reduce out. 10 minus x to the first power, and then times the derivative of what's inside, which is -1. That's our derivative. It's 1/8 x minus 1 over 2 pi times 10 minus x. So I just put this negative out here in front and turn it into subtraction. What type? We're going to have to set this equal to 0, right? And then figure out where it doesn't exist. What type of function is this? Can you all tell by looking at this what type of function it is? It's a very simple function. What's the most simple function we ever learned?
Linear.
Just a line.
Yeah, it's a line. It's linear, right? You have x to the first power. This is just a line, everyone. That's all it is, right? It's just x to the first power. It's just we have weird numbers. Okay, big deal. 1 over 2 pi. 1 over 2 pi is just a number. So I know that this never doesn't exist because linear functions are defined everywhere. So I'll never have division by 0 or anything like that. But I am going to have to set that equal to 0. So 1/8 x minus 1 over 2 pi times 10 minus x. I need to set that equal to 0. All right, I think what I'm going to do here is just convert all of these fractions to decimals, just because I think if I do that, it's going to look nicer to you. This is 0.125x, that's 1/8 x, minus, okay, 1 divided by 2 pi on my calculator is about 0.1592. Then I have 10 minus x. Okay, so all I did there was converted this to that. And now I'm going to distribute it through. So I get 0.125x minus 1.592 plus 0.1592x equals 0. We have like terms. We can put these two together. So 0.125x plus 0.1592 is 0.2842x. And then I'm going to take this to the other side. Equals 1.592. And then just divide both sides. So x is equal to, how am I doing on time? Okay, 5.602, something like that. What is this 5.602? What is that?
Perimeter of the square.
That's where we're supposed to cut it, right?
Yeah.
We're supposed to cut it there. What we don't know is whether or not this is giving us a maximum or a minimum here. We don't know. It's a critical number, right?
Right.
But remember, we're using the closed interval method, aren't we? We're using the closed interval method. So what we need to do now is take this answer along with the two endpoints and plug them into the original function, which is this one right here in blue. So that means I want to take A, plug in 0, A, plug in 10, A, plug in 5.602. The biggest value I get out is the max. The smallest I get out is the min. Let's try 0 first. If I plug in 0 here, what do I get? 0, right?
Yep.
And then this is 10 minus 0 is 10, and then square it. So I have 100 over 4 pi, which is 25 over pi, which is approximately 7.96. And that would be the area. This was in feet, so feet squared. Now we plug in 10. Watch what happens when I plug in 10. This one goes to 0, right? That goes to 0. And all you're left with is 1/16 times 10 squared. 10 squared is 100. So this should be 100 over 16, which is 6.25 square feet. And then the last thing to do is plug in 5.602. All right. I'm gonna do that for us because it's kind of a pain. I had written a program to kind of illustrate what we're doing here. All right. I just whoa. Gotta make this bigger for you. So ignore this. I don't know why I'm getting an error here. So basically we're cutting it somewhere, right? If we cut it really close to 0, we're gonna have a small square, a big circle. If I cut it further down this way, I'm a bigger square, smaller circle, right? What we found is that at, what was it, 5 point something? What was it,
602.
5.6, somewhere around here, right? Somewhere around there, we have a critical number. If you plug that in, oh shoot, it's not calculating it for me, darn it. But I can tell you it's less than 4. Okay, I'm not gonna be able to do it. This answer here that you get is less than 4 square feet. Which means we have a maximum, right? Remember, we wanted to find the maximum area. This is where our maximum is happening, right? Our maximum is happening. The maximum area we get is if we do a cut at 0, right? A cut at 0 is when we get the most area. And a cut at 0 corresponds to this scenario. All circle. Okay, all circle gives us the most area. Now, why does this convince you that a circle is better than a square? Because we compared it to the other extreme, which would be this extreme, right? That extreme is using the same wire for all square versus the same wire for all circle. And we looked at every variation in between, and we said the best way is this. You get the most area if you do it like that. Now you could do this, we're done. You could do this for any 2 objects. Like if you wanted to compare a square and a triangle together, you could say which one gives you the most area. In this case, it turns out, you can see from the graph over here, we're gonna get the most area over here on the right endpoint, which means I keep on dragging that. You wanna make the whole wire into a square. You could do a triangle and a circle. So I keep doing it. Circle wins again. All circles better than all triangle. Okay, we've just like touched the edge of the iceberg with optimization. I mean, I could go for another 8 weeks doing optimization problems. At some point, you have to go try some of these on your own. All right. In no way do I feel like I've exposed you to enough problems that you should be comfortable at all. Right. That's just the nature of optimization. So I want you to try to do your best on the homework. Use my homework solution videos to help guide you along. Let's see, we've got 4 minutes. Let me see what type of optimization. Oh, wait, hold on. I might not be able to show this to you. I'm going to say, what kind of optimization have I asked in the past? I try and keep it to something you can do like during the class, right? Like during the test. Final exam's a little different because final exam we get like almost 4 hours. So oh gosh. All right, I'm just looking to see what kind of optimization. Test is this? This is not. That's wrong. I'm not finding anything right now. I'll have to go look. All right, so what are you going to do for homework on this? Let's look at it. I'm going to tell you which problems out of here for optimization that I think you should look at. And when I'm giving you these problems to look at, I want you to keep in mind that what I'm doing is I'm trying to give you problems that are going to help you in terms of when you take your next test. These are the types of problems that I would ask. So I will highlight in yellow the ones that I think aren't really relevant. Okay, so like number 1, I'll never ask you a problem like number 1. All right, does that mean don't do it? No. Same with number 4, not really. Number 7 is a green problem, meaning yes, that is a problem you should look at, but we already kind of did that problem, right? So we already did that, so that doesn't really count. 8, we already kind of talked about. 9, I like 9. 9's good. 10, oh, I like 10. 15 is probably something I wouldn't ask. Same with 17, I wouldn't ask. 19, I wouldn't ask a problem like that on the test. 23 and 25, definitely look at. Those are going to be hard. I want to add to this, though, some more problems to look at, like 11 is a good one. So is 12. Yeah. You know that wire problem I gave you that we just did? That's actually number 27. So just so you know, like I wasn't pulling out like the craziest problem I could think of to show you in class. That's actually a homework problem. So it just goes to show you the type of like things you need to be able to think about. Yeah, I mean, that's plenty of work right there. Focus your attention on the green stuff. If you have time, hit the yellow stuff. That's it, right? Next week, we have class on Tuesday. We'll be in here doing something different, and then Thursday's the exam.
Wait, so are we doing number 27 or are you,
No, I
No.
was just saying on 27, like, because when I was doing this problem with the wire, I wasn't quite sure if people were like tuning me out a little bit, because it's like, okay, this is not a problem he would ever ask us to do, but this is actually a problem right out of the book. So this is the type of thing that is expected at least by the author of this book, that you could handle. It's number 27, so it's not even like really like one of the real hard ones. So yeah, see how it goes. Optimization. I always ask my students in Cal 2, I said, what are the things you didn't enjoy about Cal 1? They always say related rates, optimization. Those are the two things they don't like, because those are both word problems. So I understand this is a challenge, but we're here to learn. We're here to get better at these things. I don't expect you to be experts. So on the test, I will give you, not this test, it'll be the final. On the final, I'll probably give you like 3 optimization problems and say, pick one. Kind of like I did with the related rates. But you can only do one. You don't get bonus points for doing more than one.
Related rates is on this exam, right?
Pardon me?
Related rates is going to be on exam 3.
No, related rates we did a long time ago. That was, wait, is it? No, wait, hold on. No, it is
You
on this.
didn't test us over it.
I apologize. Yes, related rates are on this one. Yeah. That's the ones where it's like a balloon is growing such that the area is, volume is
it's gonna be-
growing.
2.7 till 4.4, right?
2.7 to 4.3.
4.3, okay.
Yeah. Yeah. This is going to be a beast of a test. I mean, in terms of like the amount of material on it. Of course, I can't test you on every single thing. You have to be able to do it in 100 minutes. But I think this test will be a real gauge as to, are you ready for Cal 2, Have a good weekend. Have a good weekend.
Thank
good
you.
one.
Have a good weekend.
I just
you.
have a question, like,